Hola, hi, this is Al, your probability and statistics instructor. Let's get to work. In this video, we will provide a proof of the following result. This result is related to the binomial distribution. Okay, so the statement of the result is as follows. You have a random variable with a binomial distribution with parameters n and p, where n represents the number of trials and p represents the probability of success in any of these trials. Okay, so in that case, if you're dealing with a binomial distribution, it turns out that there's a formula, an easy way of finding the expected value. And the expected value is given by n times p. Okay, so that's what we're going to be showing. Okay, let's begin the proof. As you can imagine, since we're talking about the expected value, a good starting point would be, just writing down the definition. Okay, so let's recall what the definition of expected value would be. The expected value of y would be the sum of y's possible values times corresponding probability, right? For all possible values. So that would be the first step, just the definition. So by definition, that's what we have, right? Expected value of y, sum of y times the probability that the random variable y assumes that particular value, and we do that for all possible y's. Okay, makes sense. So next step, let's plug in the expression that we have for the probability mass function, right? The formula that gives you the probability that the random variable y assumes a particular value. Okay? So, in that case, remember that the expression for the probability mass function of a binomial random variable is given by n choose y times p to the y times 1 minus p to the n minus y power. Right? Okay, so let's do that. Let's just present what the expression looks like, right? And remember that n choose y equals n factorial divided by y factorial times n minus y factorial. Okay? Okay. So we're making progress. Now, take a closer look at this expression. Okay? Note that we're doing, the sum of these products, y times probability that random variable y equals a particular value, lowercase y, for all possible values of y, and y could be 0, 0 successes, 1, 2, up to n, right? So, anyway, note that when y equals 0, 0 times this, right? So the first term of that sum is going to be 0. So let's just take that into account. That sum will start at 1. And I'm just making a note of our observation here. Hey, when y equals 0, the first term is 0. So we just rewrite the expression, but starting at 1. Okay? Okay, now let's try and simplify this expression. Okay? So remember that what we want to do here is showing that the expected value equals n times p. So if somehow we could start making those two terms n and p appear, right, isolated from this, that would be an indication that we are making progress. Okay, so let's try and simplify this. First, note that y factorial is the same as y times y minus 1 factorial, right? Okay. And also note that n factorial equals n times n minus 1 factorial. So if we decompose that n times n minus 1 factorial, then we're going to be able to pull out that n, right? We're going to be able to factor it out. So it might be a good idea to start doing that, okay? And that's what we're going to be doing. So first, the first kind of a simplification that we mentioned, we re-express y factorial as y times y minus 1 factorial. Then these cancel out, right? And then we're going to be doing the same with n factorial. N times equals n minus 1 factorial. Okay? The same trick, if you will. So we have that these cancel out. We have y minus 1 factorial, right? And then we apply the same kind of trick to n factorial. N factorial equals n times n minus 1. And now what we are trying to do is, well, if we are going to have n minus 1 in the numerator of this expression, let's make it appear somehow here below in the denominator. So we are adding a 0. So n minus 1, and then we have a 1 here. So these cancel out. So we're just adding a 0 here. But that is going to help us make that n minus 1 appear, and that y minus 1 appear as well. So anyway, then, as we mentioned before, we're going to be able to factor this out, that n, and then, as I said, adding that 0 here is going to help us have n minus 1 instead of n, and instead of having y, we are going to have y minus 1. Okay, so let's do that. I'm just using brackets to isolate this, just to underline that we have n minus 1 here, and then I factor out a minus sign here, so I have minus times y minus times minus plus 1. Okay, so another thing that we did here, note that p to the power y is the same as p to the power y minus 1 times p, right? And then we get to factor out that p as well, just like that n was factored out. Make sense? Then here, n minus y equals n minus 1. You have a minus 1 here plus a 1 here. That's just adding a 0, so it's just like doing nothing. It's something that is not illegal. Adding a 0 doesn't change anything, but then this in turn, instead of being n minus y, could be seen as n minus 1 minus y minus 1. See? Same trick for this exponent here and this term here in the denominator that was part of the expression of the combinations formula. Okay? Okay. Is it clear? Note that we already have n times p. So, if you think about it, if we could show that this sum equals 1, we are done. We're done with the proof. Okay, so take a look at this expression here. N minus 1 factorial divided by y minus 1 factorial times n minus 1 minus y minus 1, the whole thing factorial. P to the y minus 1, 1 minus p to the n minus 1 minus y minus 1. When you see something like this, you should immediately think, hey, that expression looks like the probability mass function, the formula to get the probability distribution of a binomial random variable, right? Now, what would be the parameters of this binomial? Instead of n, it would be n minus 1. And then, it would be nice if we had just, like we had before, a y. In this case, we have y minus 1, right? And something else. Remember that a binomial distribution, the possible values for a binomial random variable are 0, 1, 2, 3, up to n, right? So this one starts at 1. So if we had something, a sum that looks like this, but started at 0 up to something, then we almost have here the probability mass function. Okay? Okay, so that would be our next task, showing that this sum equals 1. And to do so, what we're going to be doing is making a change of variable. Okay, so we're going to let another variable, let's call it w, be the variable y minus 1, and see what happens, see if that helps. So let w be the variable y minus 1. So everywhere we see y minus 1, we get to substitute by aw. Okay, anyway, note that when y equals 1, then w equals 0, right? 1 minus 1, 0. No problem. Also, note that when y equals n, then w will be n minus 1, right? So we make a similar observation there, okay, with this guy. And then we're going to rewrite, instead of everywhere we see a y minus 1, we're going to write down a w, okay? So when we do that, we end up with this expression. Instead of y equals 1, we have w equals 0. Instead of y equals n, we have w equals n minus 1, right? Those are the limits for that sum. Wherever we see a y minus 1, we get to put a w. So we have n minus 1 factorial divided by w factorial, n minus 1 minus w, the whole thing factorial, p to the power of w times 1 minus p to the power n minus 1 minus w. Now, when we see this, this looks exactly like the expression you would have for a binomial with parameters n minus 1, number of trials, and probability of success, p. right? And since we're doing the sum for all possible values of that random variable w, this must go from 0 up to n minus 1, the total number of trials. Then this, that sum, is just equal to 1 because it's a binomial distribution. Okay? So that's what we write down here, that this is just equal to 1, and that's MP times 1 equals MP. And we are done. That would be the proof. We have shown that the expected value of a generic random variable with a binomial distribution with parameters n and p, where n represents the number of trials and p the probability of success, is n times p. So now if you're able to argue that a random variable has that distribution and you want to find the expected value, you could use that formula to quickly find the expected value. Okay? Well, that's it. Thank you so much for watching. Please keep working hard and take care. Bye. See you next time.